Okay, recursion. What is it all about? I actually made a poll for this as well. I want us to take the recursion poll. All right, let's take 2 minutes here. It's not a very big pop quiz, but it's something to think about. Here's some feedback from someone on the computer. Oh, it stopped.
Okay, that sounds great.
So my goals for this is to keep this relatively short and sweet. So probably won't go too deep, but I do want us to reconfirm some of the ideas of recursion. And then I have a problem set for you all to work on it. So you've actually seen it. It's from Unit 1. I've already done some of the problems, but I think you should go back and check them out some more, as they say, as the cool people say. We got 19 submissions. Let's just give it 20 more seconds. 20 submissions. Excuse me. 21 submissions. Are we going to get 100? There's 2 of you who can pump it out to 100. Slow motion. Oh, okay, well, we're going to end with that. Let's share these results. Let's check them out. Where are we at? All recursive functions can be written iteratively. 76% of people said that is true, and that is correct. All recursion functions can be written iteratively. So I know there's somebody who's yelling at their computer right now or going, well, then why don't we just write them all iteratively? I know there's somebody doing that. Great question. You can. However, recursive functions can sometimes actually be easier and cleaner to write. So even though we might not like recursion, some of us, yet because we think it's more confusing or hard, in some cases, it's actually way cleaner to write recursive. A lot of recursive functions can be rewritten iteratively using while loops or a stack. That's something to consider because every time you make a function call, it gets added onto the call stack. So you can have a real stack to act as that call stack, essentially. But it can be a little bit more complicated. Number 2, recursive problems should have which of the following? 100% of people said a base case. Cool. That is one of the correct answers in there. Half the people said an iterative step. So that's not true. A lot of recursive functions, you may need an iterative step, but a lot of recursive functions, you don't. Often, you are replacing the iteration with recursive calls. So we won't need to be iterative at all. 29% of people said a pure function. So if you recall, a pure function, this is a function that given the same inputs, returns the same outputs, and has no side effects. This is not a rule at all with recursion. You could have a recursive function that gives off side effects. So that's not true. And lastly, an inductive step. So an inductive step, that is correct. So 33% of people said that. They are correct. We need a base case. This is where we're going to have our stopping point, which we're going to talk about. And then the inductive step is the step towards moving to that base case. That's what that means. I hear a weird noise from my radiator. Okay. And last but not least, the question on here is a base case is good for 86% of people said knowing when the function should end. That is correct. So a deeper sound, I hate the treble clef. Obviously, it makes no sense. That's the wrong kind of bass. And breaking the problem into smaller problems, that is more of the way recursion acts, but it's not the base case. Okay, so I'm going to stop sharing, and we are going to go over these again. So, screen. Our recursive functions here are recursion area. Oh, I actually was looking to close this earlier. Thank you. So, what our recursion functions should have? What should they have? Base case. So this is the takes care of edge cases and tells our function when to stop. And we have an inductive step. Our inductive step merely makes a step towards the base case. Okay, so let's see an example of that. Let's pretend we wanted to write a function called the product of the array. Okay, so we have this function called product. And this is going to take in some array. And what we need to do is return product. Now, there's a couple different ways we can do this. Let's start with the first way. Okay. First way here, we look at product and we say, okay, what are some products that we know? Well, let's think about that. Let's think of how do we break this problem into smaller and smaller pieces, given that we just have this array. What's something we could think about?
In terms of steps we need to take?
I'm thinking about base cases.
So maybe a for loop that kind of iterates until you reach a certain constraint.
Okay, so we could do that as iterative. Let's think about what if we were writing recursion, right? Because if I'm doing iterative, I'm just doing return array dot reduce AC A times C, right? I'm done. But that's not the point. Our point is we want to use recursion. So we probably won't need to necessarily iterate, but we've got this big input. And we could break this input into smaller and smaller pieces. And if we did that, how would we know when we were done? What's the smallest input I can
repeat what you know if it's my internet or yours, but like it just cut out.
Sorry, Fowler?
Can you repeat what you just said? I don't know if it's my internet or yours, but like it just completely cut out everything you just said.
Okay, sure, yeah. So I'm saying we've got this big array. We don't know this. We don't really know the size of this array or what, but what can we say as we somehow make this smaller and smaller, this input? So we break this down into these pieces. What's the smallest possible array we could pass in?
Length 1.
Is it?
Or 0, an empty array.
Right, so I'm going to say that our array, if our array is empty, it would be something, right? So if I said if there's no array dot length, this means our array is empty. I shouldn't put it, I'm writing Ruby. If our array is empty, what would I want to return? Let's think about that. Put in the console what we're writing product, right? Put in the chat in 5 seconds what you believe we should return if our array's length was empty. 5, 4, 3, 2, 1. Enter. Okay, so I'm seeing lots of different answers. I'm seeing return false, return array, return null, return 0, return 1, just return an empty string, and just return. I'm getting all these great differences. Okay, can somebody tell me what product means?
It's the result of a multiplication thing, right?
Okay, right. So if I had an array that said 1, 2, 3, 4, what should this give us back?
24.
24. Yeah.
Okay, maybe so. I don't know. I haven't done the math yet, but we'll say 3 times 4 is 12, times 2 is 24, times 1, right? Good. Some of you are very quick, right? So we've got this 24. So if I'm getting something as it gets smaller, returning, let's say, a string probably doesn't make any sense because I want to return a number at the end of the day. So that doesn't help. Returning what I saw false. Again, this isn't a number, and our output's going to be a number. So that's probably not going to work either. Same with null. Same with just return. Those are all not numbers. So now it becomes a game of what numbers. So the numbers I saw in the chat, I saw some zeros and some ones. Now, if I am returning a 0, what does this mean for our product?
It's going to be 0.
Right, because anything times 0 is 0. So that's probably not that helpful. So what's a really good base case if our length was empty?
1.
Let's say 1, sure. Okay, so I'm getting like this. And yeah, I hear you. If we really sent in an empty array, you actually probably would want the number 0, right? So this is kind of an interesting question. I agree, we need a 1. But a real empty array probably could be a 0. Ugh. So maybe we can have 2 base cases. So maybe we have a base case for when there is an array that's empty, because that could probably be 0 or 1. I don't know. This is like a little, it's kind of silly because you never really solve a product problem like this. But for now, let's just say we want it to be a 1. Okay, maybe we'll fix it later. So if we wanted, when we get down to 0, to return that, how could we make our, what's the step here? What's going to go next, right? So this is where you want to write your function, your recursive functions, as if they already work, which is kind of a weird idea. But you would say like, hey, I know I'm going to call product again, and I know I'm going to pass in my array. But I need to make this array smaller somehow. Okay, so I see Doug says pop. So, okay, let's say let pop or let element equal array dot pop. So now I've got my array dot pop, and I could just times go like that. So I can just assume that this is going to work. So I say, okay, I've got my single element. My array is going to get shorter, and I've got my product. So let's try it and see if this works. So I'm going to console.log product, and I'm going to pass in our test array here. I'm going to run this file, and we get 24. We go, okay, it just kind of worked like magic. I'm
Recording film already.
sorry? What did you say?
No, that was me. Sorry, I was talking to my dad for a second.
Oh, that's fine. Right. So we've got this kind of like magic thing. Now, I think we could improve this because I do like the idea that if the array is empty to return 0. I kind of like that. But if we did that, right, our function, of course, now doesn't work. So now, what's another check we could look for if we wanted to adjust this? How could we adjust this? What could we check? Yeah, Deja says the length. What about the length? What would I look for?
I mean, the elements in the, the,
I don't know.
the length of it. I'm sorry.
No, it's okay.
I don't know. I just off the top, just to see if the length is equal to the first index or whatever, that kind of check.
Okay. Yeah, I think you're on the right. I think you're really on the right path. Which is, yeah, we can check the length still. There's still something with the length where we could say, hey, if array.length, but really, what's the length we would care about? If we don't care about 0, what's the next length we might care about?
-1.
Yeah, if it's the length of 1, perfect. Right? Because if the length is 1, well, then we could just go ahead and return our array at 0. So now we don't actually hit this base case unless we get to 0. So let's try it out. And I will also pass in an empty. So now we should get 24 and 0. And we do. And we go, okay, this function looks pretty good. So can you have more than one base case? And the answer to that
Yeah, right.
is yes. You most certainly can. It's very common, and it's totally okay. Okay, so this is a little kind of workaround we had to do because of the way multiplying works. So let's look at one more way that we could have written product. So I'm going to comment this out. And this is another way to write a recursive function where we can say product equals array. Because, well, before I actually write this, what's a possible downside of this method?
Maybe it could take a little too long to do it.
No, good guess, but I'm not too worried about the time complexity for this one. What else might ring a few bells?
Is it the first base case? Maybe I'm misreading it. But it's just saying that if the length of the array is 1, it's going to return 0.
It's going to return array at index 0.
Okay. Oh, sorry. Right. The brackets, right? Index.
No problem. What's something that's kind of funky? All right, allow me to demonstrate.
Are we not keeping track of the product now in any way?
No, that's acceptable, Jay, because this is just going to give us back the product. We are using this recursion to keep building that product already for us. So this is essentially tracking it. But let's say I write this array. And I say it's 1, 2, 3, 4. Okay. And now I'm going to say let product equal to product of array. Cool. And I will then want to map through my array for something else. So I'm going to console.log array.map, and I'll say array L, and I'm just gonna put double back of each one, each element.
Oh, you've mutated.
Hang on, Jay. Yeah, I think everyone heard it. Go ahead. Tell me what it is.
You mutated the array. You took everything out. So when you log it, the final time, it will only have one thing.
That is correct. That is correct. I want to make sure everybody is on the same page on that.
Can you explain that one more time? I'm lost.
So, as you can see, when I run this code, we get the array with a 2. Let's think about why this is happening. I've created this array variable. I've called product on my array, but then I'm just going back to my array and I'm mapping through it. So the reason of like why is because we got this sucker here, right? This is pop. Pop is mutative. We are mutating an array.
Oh, okay. All right.
So in JavaScript, it's kind of annoying because JavaScript doesn't have a great way of telling you things are mutating. In Ruby, anything that mutates something has an exclamation point at the end. So you know this is a mutative method. But in this situation, we don't know that necessarily. And so this is a totally valid answer as long as you're allowed to mutate. So when you have an interview and if they ever ask you something like this, you should probably ask them like, hey, is it okay if we mutate the array? Because if it's not, you can't do that, right? And there's ways around that, right? Like I could have easily written another function here that's like const run that takes in an array. And I can move all this junk into run. Or this would be something else. I'll write array. And then I could say let r equal, .. array. And then at the bottom, I could return run of r. Right?
You
So
have an extra R in array on line 6.
Oh, thank you. Right, so if I do something like that, I get around it. And I don't really have to change much of my logic. All I did was add a function inside my function. And in that function, I'm just making a duplicate of what I'm really running. Right? That's totally fair game. And then it's not mutating, but there is still this extra space here, or this space, or this extra time of actually duplicating this array, which really isn't necessarily a big deal, but this is just something to be aware of, right? So let's try to write product here where we're not mutating the array, and it's a little bit cleaner, let's say. So let's try this. So go back to here. Product, I'm just going to call this product 1 for now. And this should have been, I should have called run on this. Sorry. Let me make sure that that still works. Yes. Right, because I only need to make one duplicate. Okay, so in this product here, we are going to do stuff a little differently. Now we're not going to mutate. So instead, I can add another variable. So just because this takes in an array doesn't mean it only can take in an array. I could also have this take in an index. And I could start that index somewhere. Where might be a good place for me to start my index?
Maybe index 0?
Sure. So I'll make an index at 0. And when will I know that this function is done calling itself?
When it hits the base case, right? Or no?
Well, yeah. And what would make sense for this kind of a base case? If we're going to keep an index that's going to give a key into our value with each iteration, when will we know that we're done?
When I equals length minus 1.
Sure. Yeah. Right. So if I is greater than or equal to our array.length, we can just return 1. Because we've gone all the way to the end. Or we could just say when I equals to array dot length. So how do we get the 0 thing again? It's kind of like the annoying one. Well, we could just say like, hey, if there's no length. All right, hang on. Let's go back. Okay. I like the way I wrote it first. Okay, so if I is greater than or equal to array.length, we'll just return 1. However, in the event that our array is actually empty, we also still want to return 0. So I'll say like, hey, if there's no array.length, let's go ahead and return our 0. Otherwise, if our I is greater than or equal to our array.length, we will return 1. Now, we want to write this as if we've already got it a bit. So we're going to return, and we're going to call product. And we know we're going to call product on our array, and we're going to have to pass in our I. But we got to do something to our I, right? Because our I has to get closer, because this is the inductive step here. Our I has to get closer to the base case. So what can I do to I? Okay, so go ahead and in the chat and tell me what I need to add to I in 5, 4, 3, 2, 1. Blast off. Okay. Thank you. Siham, Rafid, Deja, Shia, Ohidur, Marvin, Sam, Kevin, Henry, Kong. Excellent, excellent. Ujwaka Basi, Wong, Fowler. Excellent. So I'm seeing a lot of increment. I'm also seeing a lot of I++. So I'm not sure if that will work. That does do like, that is the same as writing I plus equals 1. We don't really need to do reassignment here because each time it's called fresh. So we can really just say I plus 1. And if we do that, this should also still work. Where we get, nope, didn't work. Oh, right. So the reason this doesn't work is because we're not doing anything with our current value at I. We're just returning this 1 at the end. So we still have to say times array at I, like so. And now it works. And this doesn't mutate our array at all. So that's a slightly nicer answer. Questions on that? Okay, Tetoka Ati, it's your turn. So let's split into some breakdown groups. And I want you to write a sum function. So const sum that takes in an array. And I want this to return the sum. And I want this recursively. Okay? So I'm going to stop the screen share. Okay, stop the screen share. That's where we're at. 3s and 4s. Let's go over this together a bit. So let's take a look. So this problem is very, very similar to our last problem. And this is a problem you should probably remember. Okay, so let's think about this. So what is the smallest? Let's start it with our very base case. Let's think about what's the smallest input somebody could give us of what we would want back.
Array at 0.
Yeah.
Sure, yeah. So if our array had no length, if there was no length, we would want to return 0. Yeah, sounds fair. So I guess we'll write the mutative one first, though.
We do have it.
And so, otherwise, what's the inductive step that we have to make? What do we actually have to do? Who can tell me?
You're just gonna check it to see if it's equal to 0. Oh no, I'm sorry.
That's all right, we got that. So that's our base
Okay,
case.
okay.
If there is a length, so basically,
Yeah, go ahead. Keep going, see, huh?
if there is a length, we're gonna take the first indices value.
Yeah. Okay. So if there is a line, which is if this here, then we're gonna take at least one of the elements out of this array and check for its and then call this function again. So I could, in theory, say return sum of array plus array.pop, right? And in theory, this should work. Let's check. So we call console.log on sum of 1, 2, 3, 4, and we get okay, we got a maximum stack size. Maybe this is reading from left to right. So let's just try array.pop here instead. And we see, okay, we got 10.
But question,
Yep.
here you're mutating.
That's right, right? Here this mutates. So if I ever want to use this array again, this isn't really going to fly, right? I'm going to have to make some changes. That's a great point, Henry. So let's go ahead and write another sum version where it doesn't mutate. So let's try again. So we'll say const sum array. And we can think like, well, what's something else that we could check? If we can't mutate, we no longer will be checking if the array's length is 0. So what's something else we could be checking for?
If the array equal,
If the array dot length is greater than 1.
If so, if we're using the array length and comparing it to a specific set number that doesn't ever change, then it sounds like we'll have to be mutating, or we'll be having to check every single case forever. So what else could we add to this?
greater
What
than
else could we? Sorry?
greater than I?
Yeah, right. We could create something to keep track of what iteration we're on. So we could create an I, and we can set that to 0. And now I would be checking my array length against a variable, something that could change. So now we actually have a chance of passing it. So I could say, hey, if my array length I is less than or greater than,
Greater than or equal to I, no?
Greater or equal
if
to
I is greater than or equal to array.length, I'm just going to write it like that. It's easier for me. Then I can just go ahead and return my 0, right? So now if the array is empty, it's still going to be 0. Otherwise, I can do the same logic as before. So I can say, hey, I'm going to return my sum of my array with I plus 1 to increment my I. And I'm also going to want to add whatever comes back from that to our array at I. And in doing so, our answer should still work. And we get our 10. And now we're not mutating. So this is definitely a better answer because we're not mutating our array. And we've done that just by adding a little variable that will help us keep track of where we are within the iteration. So that's great. This is a pretty cool way of writing sum. Let's see. Is there anything else I wanted to cover? I didn't have plans to cover too deep. So there are a lot of different recursive functions. I guess we could do a couple more here. And some recursive functions, there's different types of like patterns of things you'll want. So let's go ahead and write a recursive function for factorial. So I want you to write a function called factorial that takes in a number and is going to return the factorial of that number. And if you remember, like 5 factorial is what we get back when we do 5 times 4 times 3 times 2 times 1. This is the factorial of 5. Okay, so we'll go in our breakout rooms for another 7 minutes and we will solve this one, factorial. Oh yeah, you know.
We were so close.
So close.
Victoria.
Just 1 more minute.
Tell me how this one went. Scale of 1 to 5. So I promise that the more recursive problems you do, the easier they will become, as well as the more you will like them because they'll feel more attainable, they'll feel easier. Is there any good use for fib? Good question, Ohidur. Good use? I don't know. It's kind of like the golden ratio, though. I'm sure there's something that could use it. I'm not really sure. It's more of like, the reason we teach it, it's like one of the most famous like basic recursion problems because then you can add a dynamic programming aspect to it called memoization to make it run in n time instead of 2 to the n, which is just like an insane improvement. So it's a cool problem. We won't be doing that part yet today. Okay, so I'm going to end the poll. This is where we're at. We're kind of spread between 3s to 5. Let's go over it. So let me clear this. Share screen, desktop 2. Okay, so fibs, what it's all about, right? So we get to look at, hey, what's the smallest number someone might say? They want, what's the smallest n that they could put in?
0.
Sure, right? For this problem, we would say 0. And so, and what would we want to return if it was 0?
0.
0.
0. Okay. What's the next smallest number they could put in?
1.
1. Okay. And what would we want to return if they put in 1?
1.
Okay, right? And what's the next smallest number they could put in?
2.
2, right? Yeah, thank you. And what would we want to get put out if it was 2?
It's not mine.
2.
No, we wouldn't. This is
Not mine.
we would want to put on a 1, right? So this is where the pattern breaks.
Mhm.
So once the pattern is like broken, we no longer would include that in the base case. But we can saw that for 0, we return 0. For 1, we return 1. So it's safe for me to just say, like, hey, if my num is less than or equal to 1, I can go ahead and return num. That's a fair statement. That's safe. I know that's right for the first two. Okay, cool. Now, in the event that it's not that, so if someone were to pass in fibs at 2, I can see that I have to get what I returned from 1, and I have to get what I returned when I did 0. So this is going to be made up of this fibs 0 and fibs at 1. So we start to see this pattern that my outcome for 2 is my outcome from 1 plus my outcome from 0. So if I want to just pretend that the code works and it's perfect, I'd say, okay, return fibs of num minus 1 plus fibs of num minus 2. And I go, okay, I'm going to believe that that works. And let's give it a shot. Fibs at 5. And we get 5. Is that right? 1, 2, 3, 4, 5. Yep. Let's do one that doesn't look so pattern driven. We'll do 6. We should get 8. And we go, okay, this works. Now you'll notice this is a crappy time solution, right? Even if I just put 40, it will take a while there. It took a little while. It wasn't instant. And if I put 100, it will just take so much longer. I don't know how long it'll take. So this is something negative. What's our time complexity here? Who remembers?
Would it be linear?
Linear. Would linear take this long to go through 100 things?
It'd be exponential.
No, yeah. So I hear exponential, right? If we go back to our big O lesson, we saw that Fibonacci, solved without memoization and recursively, is exponential.
Oh, right.
2 to the n. Do not forget these. These are your classic examples for your classic time complexities. So this one is 2 to the n. You can see how long this is still taking. There's no way that could be linear if it was that long. There is a way to make this linear that maybe we can do another day. I don't think it's important to go over it today. But you should know that there is ways for us to do that, and that's more by keeping track of things we've already checked. So if we've already visited this number, we can just return exactly what that number returned to instead of re-go down the rabbit hole to find out what that number gives us. Okay, I'm gonna just kill this. The 100's not coming back anytime soon. Okay, and for the bonus question, did any team get through the bonus question?
I did it.
Yeah?
Yeah.
Awesome. You want to walk me through it?
I could just send you the code.
Nope. I have the code myself.
Nah, you got it.
Okay. Right, so there's a few different ways I could do this. And so let's try out some. So we'll say const, let's call this fib array. Right, this is taking in some num, and I can do something with my fibs. So maybe I have a fibs item here that is starts at a 0 and a 1. Right, and if I do it like this, I could say like, hey, if my number is less than or equal to my length, like my fibs.length, well, then I'm already done. And I can just go ahead and return fibs.slice from 0 to num. Right? Otherwise, I want to do some stuff. So maybe I'll take the last two numbers here and push it in. So I could say, okay, I could say fibs, if fibs dot length minus 1 plus fibs at fibs dot length minus 2. And this could be our variable for next fib. Right, never tell a fib. And we can just go ahead and push this into our fibs. So I'll say fibs dot push our next fib. And then we can just go ahead and call our function again by calling fib array on our nums and pass in our fibs. And if we do that, it should also work. So we could say console.log and we can call fib array, pass in our number 5. We'll see the first 5 elements, and we do. Right? So there's a lot of different iterations and variations of this. This could be written in other ways. Henry, is this how you wrote yours?
Nah, it's not.
Oh, interesting.
I just, the way I wrote the function const fib array, and inside I just put one argument nums, and I put that fibs that you have on line 60.
Mm-hmm.
I actually I put I put my base case as if num equals 1, return an array of 0, 1.
Cool.
Yeah.
Maybe you can throw that in our Slack channel so everyone can see
Yeah,
it.
I'll throw it in.
Sweet. Okay, so this is recursion. Any questions on anything that has to do with recursion?
Yes. I have a question in line 60.
Okay.
I don't understand fibs 0 and 1. What do you mean by it?
This is a default argument. So our Fibonacci's always start with a 0 and 1. And I have no good way of deriving that besides just knowing that. That's my base case. And so I'm just setting this as a default. So because I'm not expecting the user to actually pass anything in here, I'm just expecting them to pass in a number.
Okay.
And then I can check to see if that number is less than this current length. So if they just pass in 1, my length is 2 here. I'll just slice from 0 to 1, and I'll take that element.
Okay. Thank you.
No problem. Okay. Any other questions? Great. Then let's just try this poll one more time. This recursion poll. And tell me what we've got. Just waiting on a couple more. I love these mixed nuts, specifically the Brazilian nut. I didn't know I liked the Brazilian nut as much as I do. All right, let's end the poll, share our results, see our improvement here. 100% of people said that recursive functions can be written iteratively. Awesome, that's correct. Everyone still knows the base case is correct. This time, 67% of people said inductive step. That is correct. Iterative step, pure function. Nope, that's not correct. Pure function means that it can't have side effects, so it couldn't mutate. We saw recursive functions today that did mutate, so may not be the best practice, but it is something that is allowed. Iterative step. Iterative means we are iterating, so going through something, which we didn't have. It doesn't need to have that. And everybody got what the base case does now. Okay, so we got some improvement. That's cool. That is everything I wanted to go over.